right, well, good morning, everybody. So first, just a reminder that some of you didn't pick up your homework last week. Please don't forget to pick it up. Also, don't forget that last week's homework is all due on Wednesday, so please bring that with you. And of course, the new homework set from Chapter 9, this is a homework for the entire week. Now that we're not doing review anymore, I'm not going to have these really large homework sets like I did the first couple of weeks. But nonetheless, these are important problems, so please make sure you write them down. And please note also that the comment I have there in the big square brackets only deals with problem 119. So I don't want you to solve it exactly as identified in the book. I want you to do it that way. So please make sure you add those terms. Now at this point, you don't even know what epsilon means. We'll get to that, of course, before the end of the week. A to C, A to T are just isentropic efficiencies for compressors and turbines. But nonetheless, that's the homework assignment for the week. And let's just get back to what we were talking about last time. So please remember that we're still dealing with gas power cycles here. We're still dealing only with the air standard type of cycle. We still understand that as we solve air standard cycles, we could either choose to solve them a little bit less accurately, that is using constant specific heats, or a little more accurately, which is to use the variable specific heats. And of course, along with that is data from table A17 for air. Now, we've discussed at this point just two cycles, right? Both are reciprocating engine cycles, one being the Otto cycle, the other being the diesel cycle. We've seen example problems for both, so hopefully this material now makes sense to you. Those cycles are reasonable models for real internal combustion engines, okay? Both gasoline and diesel engines. But now we need to start looking at other models, and these other models are going to be applicable for other types of engines. The next one, actually the next two that we're going to look at are cycles that really are very, very limited in their practical use. In fact, I'm not even going to discuss them except for just a little bit of very, very brief theory. These are called the Stirling engine and the Ericsson engine, okay? So we'll just start with the Stirling. And quite frankly, I probably shouldn't call it engine at this point. I mean, granted, these are all heat engine cycles, so it's not incorrect to call it an engine, but we're really just talking about the thermodynamic cycles now. Now, the Stirling cycle, like the Ericsson cycle, are rather unique in that they're gas power cycles, yet the heat transfer takes place at constant temperature. So, heat transfer at constant T. Now, as you think about that, that's practically impossible for us to do in the real world. It's not that it can't be done, and certainly there are some Stirling engines that have been built, but if you have a gas and you're transferring heat into it, then typically your temperature is going to rise, right? Or if you're transferring heat away from it, then the temperature is going to drop. To try to transfer heat and maintain constant temperature is very, very difficult. In fact, at least in my opinion, the reason so few Stirling engines are actually out there is really because of that fact. There really are not good ways to make Stirling engines. Now, again, that doesn't mean there aren't some Stirling engines that exist out there. There's some solar Stirling engines. They're interesting devices, but again, they're not particularly practical, so I'm not really going to go through them in any detail. I will note that the heat transfer does occur at constant temperature. I would also note that the work which is done is actually going to be done at constant volume for a Stirling cycle. Which I might note is also rather problematic, okay? When you're doing work, typically you've got some sort of expansion taking place. You're basically increasing the volume. That's typically what would happen. If you're doing work, that is, you're taking energy out of the fluid, then typically that would imply that the pressure is probably dropping, as is the temperature, and the specific volume is actually increasing. But again, in the Stirling cycle, we have to set this engine up so that work is done at constant volume. Again, this is very, very difficult to do in practice. So again, for these reasons, I'm not really going to spend a whole lot of time on this. I will plot the cycles on both the TS and the PV diagram. On a TS diagram, we would typically have something that would look like this. Okay, so we're basically starting, at least in this cycle, at some elevated temperature, 0.1. And now we're going to add heat at this constant temperature. So this is our heat in. Then we're going to have some work output. We're then going to reject heat, also at constant temperature. And then we'll require some sort of work input. On the PV diagram, we would start at 1 and go to 2 in this fashion. Okay, so the volume is actually going to be increasing. Then we're going to go through the constant volume work process. So there's constant volume, just a vertical line. Then we're going to have our next constant temperature process, where we're going to reject heat. And then lastly, our work input from 4 to 1. Okay, so work in and work out, heat in and heat out. Okay, so you can pretty clearly see what's happening here, all right? Again, constant temperature, horizontal lines on the TS diagram for the heat transfer processes, and constant volume for the work processes that we can see pretty clearly as vertical lines on the PV diagram. Okay, and nonetheless, that's really all I want to discuss with regards to this. In fact, I might note that even in your textbook, the author really doesn't cover these engines in any significant way. They do develop an equation for thermodynamic efficiency, but it's a very simple equation. And again, in this class, I'm not even going to worry about that. All right, so what about the Ericsson engine? Or again, I should call it Ericsson cycle. Okay. So really the big difference between the Stirling and the Ericsson is the way the work is done. The heat transfer is still done at constant temperature. But the work is done at constant pressure. Okay. So once again, this particular type of cycle is not particularly practical in the real world. In fact, quite frankly, I've never really seen any engines that are designed based on the Ericsson cycle. I assume that they exist out there. I mean, every thermo book that I've seen talks about the Ericsson cycle, but you just never hear about an engine that operates on this cycle. Once again, though, let's just show it on the appropriate TS and PV diagrams. Once again, we'll start with state point 1 at our high temperature. Heat transfer as we go on a horizontal line from 1 to 2. Then we have constant pressure work from 2 to 3. And then constant temperature, heat transfer out of the system from 3 to 4. And then work input from 4 to 1. Okay? So it actually looks very similar to the TS diagram for the Stirling engine. The big difference is that these are actually constant pressure lines and they're not constant volume lines. Anyway, let's just show the heat and work terms. And then let's show the same thing on the PV diagram. So here, our point 1 is going to be over here. We're going to add heat at constant temperature. This brings us out to point 2. We're then going to have work at constant pressure over to point 3. And then more heat transfer at constant temperature up to 4. And then lastly, our work input from 4 to 1. So work in, heat in, work out, heat out. And these are the basic processes associated with the Ericsson cycle. Okay? So ultimately, if one were to calculate the thermodynamic efficiency, and this would apply to both Stirling and Ericsson, you can actually see this derivation in the book, but it's a very simple equation. It's just 1 minus T low over T high. Okay, so this is how we'd calculate thermodynamic efficiency for this type of cycle. Now note, this would be for the ideal case. Certainly if you have a non-ideal case, which is definitely not even mentioned in your textbook, then the analysis is going to be quite a bit more complicated. The thermal efficiency is not going to be just a function of temperatures. But nonetheless, this at least gives you something to think about with regards to these two cycles. And with that, I'm actually going to move on. Whoops, lost my notes. Thank you. So are there any questions on these cycles? Probably not much to ask since I really haven't discussed much. Now let's move on to a cycle that is of use to us. In fact, it's a cycle that was covered, hopefully, in your ME 301 class, and this is the Brayton cycle. So first of all, just by show of hands, how many of you have never covered the Brayton cycle? It just didn't get covered in your 301 class. Okay, so everybody's been exposed to that. And you're supposed to be exposed to just the simple Brayton cycle in your 301 class. And hopefully you're also exposed to both the ideal and not ideal Brayton cycle. But let me go through just some basics here so that we remember what the Brayton cycle is all about. And in fact, while I'm talking about this, these are just some, well, vendor literature that has some nice diagrams on the inside that actually shows cutaways of a gas turbine engine, which is what the Brayton cycle is used for modeling. So let me just pass one around each side. So as we're talking about this, you can see what a real engine would look like. And basically, these are jet engines, okay? Whether they're stationary jet engines, in other words, they're stuck to the ground and they're just spinning an electric generator, or whether they're jet engines on the wing of an aircraft, it really doesn't matter. From the standpoint of analysis, they're both analyzed exactly the same thing. Frankly, we don't really care how the network is used, just that it is somehow used, right? We, as mechanical engineers, would probably be more interested in a stationary gas turbine engine. On the other hand, if you're an aerospace engineer, then perhaps you'd be more interested in a jet airplane and that kind of an engine. Note that on a jet airplane, you're just spinning a turbofan. That fan creates the thrust needed to move the airplane through the air. On a stationary application, you're spinning an electric generator. But again, that's just a network. That really doesn't matter. So, Brayton cycle. Now, the Brayton cycle is not a reciprocating engine cycle, right? It just isn't. This is a series of steady flow devices that are all stuck together end to end, if you will. The net result being the ability to produce work, having given some heat input. I mean, that's what heat engines are all about, right? So this is not a reciprocating engine cycle. This uses many steady flow devices. Okay. And perhaps the best way to begin something like this is just to show a nice, relatively simple schematic. So again, this is just the simple Brayton cycle. And in a typical simple Brayton cycle, we'd start at state point 1, and we would enter a device that's called a compressor. So I will often just use a big capital letter C, but I'll just write the word compressor for now anyway. So work input is certainly going to come into this compressor. In other words, the air that's moving through the compressor is going to have work done to it, and it's going to compress the air, right? It's going to go to a higher pressure and temperature. So that's our work input. Sometimes we would just write this as W sub C, C meaning compressor, rather than just writing the word in all the time. So C here represents the compressor's work input to the cycle. Now the air that comes out of the compressor has to have heat added to it. So here we have our big heat exchanger, and certainly there's going to be heat input. By the way, I'm just using lowercase letters Q and W. It's not necessary. You can use capital letters. You can use letters with dots on top of them, as long as you understand that we're talking about heat input or work input or whatever. But nonetheless, the heat input in our cycle is assumed to be just heat input in a heat exchanger of some sort. Okay? In the real world, that's certainly not the case, right? In the real world, we have a combustion chamber. We're actually mixing fuel with the air, and we're burning it until it achieves a very high temperature, and that high temperature gas is now going to move into the turbine section of this system. But of course, this is an air standard cycle, right? We're only dealing with air standard cycles, so we simply have air that's circulating through this cycle. We're simply assuming that however much heat that would otherwise be liberated by the combustion process is simply being added by the heat exchange process. In fact, isn't this the same thing that we assumed when we were looking at the Otto and diesel cycles? Yes, of course it is, right? These are closed cycles where there's just air moving in a loop. There's no intake, there's no exhaust, there's no fuel-air mixtures that are burning. They're relatively simple air standard cycles. Nonetheless, the heat input goes into this device. I'm still going to call it the combustion chamber. Sometimes we might just call it a combustor. And often I'll just use CC as an abbreviation for combustion chamber. But again, from our analysis, it's not really a combustion chamber anymore. It's just a heat input device, a big heat exchanger. All right, so now we leave this device at point 3, and now we're going to enter the turbine. So big T for turbine. Of course, the turbine is a work output device. The very high temperature, high pressure gas that's leaving the combustion chamber is going to go into the turbine. It's going to cause it to spin. It's going to give up its energy. Its pressure and temperature are going to drop. Therefore, its specific volume is going to rise, or if you will, its density drops. And we leave this particular device then at point 4. By the way, the work output as it's out from a turbine is often just shown as WT instead of writing the word work out. So this is the turbine work output. And then lastly, what leaves the turbine is still going to be at an elevated temperature. We have to reject heat from it. So here is another heat exchanger. And this heat exchanger is, again, not really a heat exchanger. In the real world, this is just the environment. You're taking those exhaust gases from the turbine and you're simply dumping it out into the environment. The environment is so huge compared to the small amount of exit or the small amount of output from that turbine that we assume that that exit from the turbine eventually cools down until it's at the same temperature as the environment. Okay? So this is the environment. Again, in the real world, it's the environment, but in our world, it's just a heat exchanger. And this is where we're going to reject heat from the system. So here's our Q out term. Okay? So this is the simple Brayton cycle. Now, another thing that I might note is that in our real world, you should at least understand what these engines look like, even though we're modeling them in this nice, simple, closed manner. In fact, that's why I've passed those 2 handouts around. You can see that a real gas turbine kind of has this kind of a look to it. On this end of the turbine, these are the various stages of the compressor. So these blades are all compressor blades. So this is our compressor. As the gases move through, again, in our case it's air, but they're really gases. You know, air is a mixture of various gases. But we move through the compressor, we'll actually add fuel, and this is our combustion chamber. Okay. So again, in the real world, fuel is injected, the fuel and air burn. And then, as we continue, again, noting this is a single shaft, so the compressor is spinning, but it's spinning under the influence of the turbine. And now we'd show all the turbine blades on this end. So this is our actual turbine. And then we have our discharge. So this would represent point 1 over here, entering the compressor, right? This would represent point 2 as we leave the compressor and enter the combustion chamber, right? So maybe I'll also show, here's my work input. We go to the combustion chamber, here's the heat input. So we pass through the combustion chamber. Combustion is finished, and we get to state point 3. And then at state point 3, we pass those gases across the blades of the turbine. The turbine spins. Now, this is, again, a single shaft, right? So the work produced by the turbine, much of it is actually being used by the compressor. The difference between the two is the net work output. And then this shaft would be connected to something else, okay? If this were a stationary gas turbine engine, then it's connected to an electric generator. We could show a generator attached to the backside. Sometimes the generator's on the front side. If it's an aircraft engine, then the shaft will be hooked to a turbofan. In fact, the fan's never going to be on the backside. The turbofan's on the front side. And that's actually what you see when you're looking into a jet engine. You know, usually they'll have something like a smiley face or a yin-yang or something painted on the front side for no apparent reason, just to be funny. But that's the turbofan you're looking at. That's spinning under the influence of the net work from this Brayton cycle, and it's, well, producing thrust, right? The fan blades are moving air at an incredible speed. It passes actually around this section. It accelerates, shoots out the back, provides thrust. Again, that's not really important from our analytical point of view, but you should understand what we're thinking of, what we're talking about. Anyway, so we leave at point 4 over here. And then, again, in the real world, we're done. It's not really a cycle, right? We have new fresh air coming in at the ambient conditions, and we have new exhaust going out. But in our world, we have the whole environment, and we're simply removing heat from our system into the environment, and that brings us right back to the thermodynamic state at point 1. So this is our gas turbine engine. This is our Brayton cycle. Now, one other thing I might want to note, just as a reminder, is that the work that's done in a Brayton cycle is done at constant pressure. So, constant pressure work. And this would be both the work input and the work output, right? The work output from the turbine is done at constant pressure. The work input to the compressor is done at constant pressure. So we have constant pressure work. And then also note that in the ideal case, we have isentropic. I'm sorry, I just totally wrote the wrong thing there. It's the heat input that's done at constant pressure, right? Not the work. The work is done as the turbine spins or as a compressor spins, and those are, in the ideal case, isentropic processes. So I should have said that we have constant pressure heat transfer. So sorry about that work thing. Constant pressure heat transfer. Okay. And in the ideal case, anyway, we have isentropic work. Okay. Now, we will talk about both the ideal and the non-ideal Brayton cycle. Okay. In the ideal case, well, it's isentropic work. In the non-ideal case, what do you suppose we have to use? Well, isentropic efficiencies for these steady flow devices. This is something that was covered, what, chapter 9, I guess? No, chapter 7, right? Chapter 7 of your thermo book. So we're going to have to figure out not just how to deal with the ideal case, but also the non-ideal case, and we'll get to that here shortly. So with all of this in mind, let's now show the thermodynamic property diagrams. Okay, I'll make it easy on myself. Okay, so we have a TS and a PV diagram that should be shown, and we'll start with the TS diagram. So in a typical Brayton cycle, and again, this is going to be our simple ideal case. We'll start here at point 1. So this is going to tend to be the lowest pressure and lowest temperature portion of the cycle. This is just the ambient air in the real world, right, that comes into the engine. In our case, it's down here at point 1. And now we go through isentropic compression. That brings me to point 2. So again, this is isentropic. I'll just put ds equals 0. And this process is the work input process, right? So work input. Why don't I just put WC now, because we know that the work input is through a compressor. Okay. On the PV diagram, this whole process would go from 1 to 2 like this. Okay, so as you compress, certainly the pressure is going to rise, but also the volume is going to shrink. So that will be the first process. Now we have our heat input process. So the heat input is done at constant pressure. Although being done at constant pressure doesn't mean that it's done at constant temperature, right? It's a constant pressure process, but as we add heat, the temperature is going to rise. So we get to point 3. This can also be shown as a horizontal line on the PV diagram, right? Constant pressure heat input. So here is our Q in. And now, in the ideal case, again, we go through the expansion process to the turbine. And I often call it expansion. It is expansion, right? The volume is increasing. The gas, in this case our air, is actually expanding. So turbines do cause the air to expand and produce work at the same time. Anyway, so we go from 3 to 4. This would be our work output from the turbine. So again, I'll just put WT for turbine. And again, this is isentropic. So let's put a ds equals 0. In fact, maybe on the line from 2 to 3, just for clarity, why don't I just put dp equals 0, since there is no pressure change from 2 to 3. I mean, that's obvious just looking at the PV diagram. It's a horizontal line, but still, I'll put it on the TS as well. All right, so back to the PV diagram. The isentropic process allows the pressure to drop back down to the original pressure at point 4. And then last but not least, we have our heat rejection, our heat output. So this goes from 4 to 1. This is also done at constant pressure. So by the way, when we look at the real world, there's nothing that our exhaust from this engine is going to do to change the pressure in the environment. I mean, the environmental pressure is the environmental pressure. So clearly that heat transfer process is done at constant pressure. Nonetheless, from 4 to 1, we have another horizontal line. And that's what the process would look like on these two diagrams. Now again, I could show the various work terms, the compressor work input, turbine work output, heat input, heat output. But nonetheless, these are the diagrams that you would generally use, to help illustrate these types of cycles. Okay. Now, what about the thermodynamic efficiency? Like all problems involving heat engine cycles, it's the thermodynamic efficiency that's really of interest to us. At least it's one of the things that's of interest to us. This gives us our best measure of how good that engine is at turning heat into work. I mean, that's what thermal efficiency, right? It's the net work over the heat input. So the more efficient the engine, the more heat is being turned into work, and that's best for us, right? We're able to sell more work to our customers, so perhaps we make more profit, or we can think of it as buying less fuel from our suppliers, so we have lower expenses. But that's the whole idea behind efficiency, right? The higher the thermal efficiency, the more economical your engine is, and you're trying for that, right? I mean, you're engineers. You're trying to minimize what your clients are going to have to pay for the work that they're producing. You're trying to maximize their benefit, in other words, the work that they're able to sell to their clients. So this all makes sense. So what would the thermal efficiency be? Well, it's no different than the thermal efficiency for any other heat engine. It's just the net work over the heat input. And of course, the net work is just the difference between the work out of the turbine and the work into the compressor. And again, divided by the heat input. So this is something that we would be using on a regular basis. Also, let's note that this could, again, be written in a variety of ways. If we have, capital letters, in other words, if we want the total amount of work by the turbine less the total amount of work by the compressor over the heat input, that would be an appropriate equation. Or it could be written as a rate equation, right? We can have the rate of turbine work, so W dot T, in other words, the power produced by the turbine minus the power required by the compressor, W dot C, divided by the rate of heat input. And quite frankly, it's this final form of the equation that is very often used. I mean, after all, these are steady flow devices, right? There's a certain flow. In a real engine, there's a certain flow moving through it, right? We have a certain rate that fuel is being added and thus burned, so we have a certain rate of heat input. We have a certain rate that the air is flowing through the engine, thus we have a certain power. Rate of doing work is power, right? So this form of the equation is very common. And of course, this form up here on a per unit mass basis is also very common. Okay. So hopefully you all remember this from your previous thermo class. One other thing I just want to define as we start looking at some of these equations is a ratio that's different than the compression ratio. When we looked at compression ratio, that applied specifically to these reciprocating engine cycles. But now we're actually interested in a pressure ratio. We know that there's a certain maximum pressure corresponding to heat input and a certain minimum corresponding to heat rejection. So that pressure ratio is important to us. It's something we'll use all the time. So we'll just define RP as the maximum cycle pressure over the minimum cycle pressure. And you can see that that's either going to be P2 over P1, or it's going to equal P3 over P4. Okay, but this is a pressure ratio. Okay, it's not a volume ratio, and we need to just recognize this. This is one of the big differences between our reciprocating engine cycles, right, where we always use the volume ratio called compression ratio, and the Brayton cycle, which uses pressure ratios. Okay. All right, so with all this in mind, what are the equations now for the work and the heat transfer terms? And I'm just going to show everything on a per unit mass basis. First, I might just note that these are steady flow devices, right? So for a steady flow device, let's also note that there's not going to be any kinetic or potential energy change to deal with. Like most engine cycles, we purposely keep the velocity down. If the speed gets above about 10 feet per second, which is what, 3 meters per second or so, then you'll find that even a gas like air can start to erode the inside surfaces of your engine, including your turbine and compressor blades, and we just don't want that to happen. So we purposely leave the speeds on the low side. As such, we're going to have essentially no change in kinetic energy. And for that matter, these engines are generally horizontal in their orientation. There's no significant height difference between the inlet and the exit, so there's no potential energy change. And of course, in the ideal case, the work that is done adiabatically reversibly, in other words, without any heat transfer, right? So that in the ideal case, there's no heat transfer with the work terms. And for that matter, when we talk about the heat transfer terms, the heat transfer process would also be done with no work being done. Okay, so there's no work during heat transfer. So no work during the heat transfer processes. So what does that give us with regards to our first law of thermodynamics? Well, these are steady flow. They're all single stream steady flow, I might note. So our basic equation is heat transfer minus work equals change in enthalpy, right? Plus change in kinetic energy plus change in potential energy. But for the heat transfer, there's no work nor kinetic or potential energy. And for the work, there's no heat transfer nor kinetic and potential energy. So the terms just end up being functions of enthalpy alone. So again, this was discussed hopefully at length in your previous thermal class. So we would note that the heat input then is just going to be the difference in enthalpy between 2 and 3, so H3 minus H2. The work input, which is our compressor work input, is just going to be the enthalpy change from 2 to 1, really from 1 to 2. By the way, another reminder that all of these heat transfer and work terms are all magnitudes, that is, are all absolute values, just like they were previously. Again, we're still talking about these same air standard cycles. I mean, it's a different cycle, but the same air standard kind of assumptions. Nonetheless, so we have our heat transfer, we have our work input. We know that work input is really negative just because of our sign convention, but again, this is the magnitude. We also have our work out, which is our turbine work. So this is just going to be the enthalpy change from 3 to 4. So H3 minus H4. And then I suppose if we really wanted to, we could just show the net work. And of course, that's just the difference between the compressor and turbine work. Turbine and compressor work. So H3 minus H4. And then minus H2 minus H1. And again, please note that the minus sign within the equation takes care of the actual sign of the compressor work term. H2 minus H1 is the magnitude of the work. The minus sign gives us our direction. All right, so these would be the general equations we would use. Now, at this point, we actually need to start thinking about our two different methods of solution. Okay? If we had variable specific heats, well, then we just use the equations that are presented here on the board. So just use the equations above. And of course, the data you're going to get is going to come from table A17 or A17E. So you're certainly going to use the data from A17. Let's also keep in mind that you're going to have to use relative pressures now. Remember that when we were looking previously at the reciprocating engine cycles, again, Otto and diesel engine cycles, if we use the method of variable specific heats, then we used relative specific volumes because we were always given compression ratios, right, which are volume ratios. So we had to recognize that for an isentropic process, the ratio of volumes equals the ratio of relative specific volumes. Here, it's a Brayton cycle. We have pressure ratios now, not volume ratios. So we need to make sure that we use the relative pressures because after all, for an isentropic process, the pressure ratio is equal to the ratio of relative pressures.
So yes. Is just PR the same thing as RP over here?
No, R sub P is a pressure ratio. This is the maximum over the minimum. This is PR. This is our relative pressure. This is the data that exists in table A17. And frankly, it's not even a pressure term. They call it relative pressure, but it's really an entropy function, and it's only a function of temperature. Nonetheless, it's called relative pressures because the pressure ratio equals the ratio of relative pressure, so we just use the word relative pressures, but it's not a pressure term. Anyway, we're going to use relative pressures for the isentropic work processes. Okay. In other words, P2 over P1 is going to be PR2 over PR1, and similarly, P3 over P4 is PR3 over PR4. And by the way, P2 over P1, it is the pressure ratio. So the pressure ratio is P2 over P1, is PR2 over PR1, or that pressure ratio is P3 over P4, which is equal to PR3 over PR4. So we're definitely going to have to use this. Now, I will give you an example problem here eventually that helps illustrate this, but we're not quite ready for that yet. Okay, so any questions just in general about this? The other case, of course, would be for the case where we have constant specific heats. Okay. So if we have constant specific heats, okay, then what do? Well, we can't really use these equations above anymore. Here they are. But certainly we understand how to adjust them. We know that an enthalpy change is just Cp times a temperature change. We just know that already, so we'll utilize that. So let's just look at each term in turn. The heat input, instead of H3 minus H2, is just going to be Cp times T3 minus T2. The work input in the compressor is just going to be Cp times T2 minus T1. Again, note these are enthalpy changes, so we have to use Cp, not Cv. Cv only applies if we're dealing with internal energies, and we have no internal energy change terms at all anymore. That's just for your reciprocating engine cycles. We have our work out, our turbine work. So this is just going to be Cp times T3 minus T4. And of course, the net work is just the difference between the two. So we could just factor the Cp out entirely and get T3 minus T4 minus T2 minus T1. Okay. And of course, the general equation for the thermal efficiency, that doesn't change. I mean, that's still just the net work over the heat input, so we'll still use that as is applicable. And then something that should also be noted is that we can modify these equations a little bit in order to find a simpler version of our equation for the thermodynamic efficiency. We did something similar when we looked at both the Otto and the diesel cycles, right? We had a efficiency equation that was in terms of work and heat transfer, but through manipulation, we were able to adjust that equation so that it was only in terms of a volume ratio term. That's what we did for the reciprocating engines. Now we're going to do it, and hopefully we'll get an equation that's only and entirely in terms of just the pressure ratio. So let me just go through that very briefly. These are the general equations. I don't want to change those, but I do want to just make a couple of notes here. If we look at the work out and the work in terms, what I want to do is I just want to factor a T1 out of the work in term, and I'm going to factor a T4, a T3 out of this work term. So for work in, we get CpT1 times T2 over T1 minus 1, and here for T3, we get 1 minus T4 over T3. Oh, in fact, I think I did not do that right. I actually want to factor out a T2, not a T1, so let's just modify this compressor work term. So the T2 comes out, and then we have 1 minus T1 over T2. All right, so that's how it's supposed to be. Now, I'm just going to continue this little derivation below here. All right, so we have the Cp and we have the T term. So we have Cp times T2. And now let's just note that isn't the process from 1 to 2 one of those isentropic processes? Yes, it is. And for an isentropic process, when we have an ideal gas with constant specific heats, we would note that the temperature ratio is going to equal the pressure ratio raised to the k minus 1 over k power. So, this should just be below that in your notes, but let's just keep that in mind, that T2 over T1 is going to equal P2 over P1 to the k minus 1 over k, right? This applies only for the isentropic process when we have an ideal gas with constant specific heats. And of course, P2 over P1 is just our pressure ratio. And then the same thing between points 3 and 4, right? So again, this is an isentropic process, and as such, the temperature ratio has to equal the pressure ratio to the k minus 1 over k. And of course, P3 over P4 is the pressure ratio. So these now can actually be subbed in to the temperature ratios that are over in those equations. So again, isentropic. Plug in above. So I'm just plugging them right back in here, right? So instead of T1 over T2, please note T1 over T2 is the same as 1 over T2 over T1, which, as we can see, is just the pressure ratio to the k minus 1 over k. And the same thing for the turbine. So we have Cp, and the T3 is factored out. And then again, 1 minus, and this is the same, right? T4 over T3 is the same as 1 over T3 over T2, which is, again, the pressure ratio to the k minus 1 over k. Okay. And now, if we would like to, we can simply throw these into our efficiency equation. So I guess I need another arrow here. Plug into thermal efficiency equation. Okay, so the net work over the heat input is what has to go here. So again, what is our net work? Well, let's just plug in these various terms. You can see that both terms have a Cp in them, and both terms have a 1 minus 1 over the pressure ratio to the k minus 1. So I'm going to factor those out of both terms, and we'll just end up with T3 minus T2 times 1 minus 1 over the pressure ratio to the k minus 1 over k. So there's our numerator. And don't want to forget my Cp. And then what about our denominator? Well, it's the same as those first terms in the numerator, isn't it? The heat input from 2 to 3 is just the enthalpy change, which is a Cp times the temperature change. And you can see that all that cancels. And we end up with exactly what we were looking for, which is an equation that's only a function of the pressure ratios. So this is going to be the easiest way for us to calculate the thermodynamic efficiency for this particular type of situation. Now again, keep in mind that this is specifically for the ideal Brayton cycle, okay? Not the non-ideal Brayton cycle. Once we move on to non-ideal, then everything changes. And of course also this is only for the case where we have an ideal gas with constant specific heats. One other thing I might note, this pressure ratio to the k minus 1 over k is still equal to the associated temperature ratio, right? Oh, in fact, I think I have it up here still. So we could just sub in this ratio, T2 over T1. So 1 minus 1 over T2 over T1 is just 1 minus T1 over T2. So this is another simple equation that we can use in order to calculate the thermodynamic efficiency. We don't absolutely need our thermodynamic properties at every state point. We only need either the temperatures across the compressor, T1 in, T2 out, or we need the pressure ratio across the system, and then we can find the thermodynamic efficiency. Now, one reason I'm spending so much time going through what I really think of as mainly review is because we're going to have to use all of this when we start looking at modifications to the Brayton cycle. And there are several modifications that we're going to look at, every one of which is designed to improve the thermodynamic efficiency. I mean, that's what it's all about again, right? We talked about that earlier. If we can improve the efficiency, then we're able to get more work out for each unit of heat input, and that's really our best desire. So we'll get to that eventually, but not yet. What about the non-ideal case? So we're still looking at the simple Brayton cycle. In other words, we still just have a single compressor, a single heat input device, combustion chamber, a single turbine, a single heat rejection device. You know, that doesn't change. But the way we analyze it now is going to be a little bit different because we're now going to look at the non-ideal case. Right, so now we're going to look at the simple but non-ideal Brayton cycle. Now, quite frankly, there's no reason for me to redraw the schematic diagram. I'm only changing the way that I analyze the cycle. I'm not changing its physical configuration. We still have our compressor, we still have our combustion chamber, we still have our turbine. None of that changes. We're just analyzing a little bit differently. When it says non-ideal, basically that means that it is not isentropic work. Okay. And the way we deal with non-ideal behavior for a steady flow device like a turbine or compressor is through the use of isentropic efficiencies. So this is not isentropic work anymore, and we must use the isentropic efficiency. And of course, this is going to be the isentropic efficiency for both those devices. That is of the compressor, which is just eta sub c, and the turbine, which we call eta sub t. Okay, so that's really the big difference. Now, I do want to redraw the TS diagram. I'm not going to bother with the PV diagram. The TS diagram really illustrates what I'm trying to show here. What I would typically do as I draw this is I would show the minimum and maximum pressure lines. And on a TS diagram for an ideal gas like air, the constant pressure lines angle up in this fashion. So this is the low pressure in the cycle, and this is the high pressure. In fact, instead of using the words high and low, why don't I just say minimum and maximum? So the lower line is the minimum, and the upper line represents the maximum pressure. We also know that as we go through the compression process from point 1 to 2, we're going to have to analyze it in two different ways, right? First, we assume that it is indeed an isentropic process. So we're going to go from 1 to 2 vertically upwards. And then once we have solved this part of the process, then we're going to apply the isentropic efficiency of the compressor to determine the actual discharge conditions from this compressor. So the actual process goes from 1 to 2 along the solid line. There's definitely an increase in entropy, right? We know that if it were ideal, it would be like the dashed line, just a vertical line. After all, ideal would represent isentropic. But this is not ideal anymore. So the entropy will increase, and we'll end up with a state point 2 above and to the right of state point 1. Now, please note that the pressure doesn't change. I mean, I know what my maximum pressure is in the cycle. I know what the minimum pressure is in the cycle. I don't need to identify a different pressure associated with each of these state points too. It's constant pressure at the discharge, right? That's the maximum pressure. It's just P2. But what I do need to do, though, is put a subscript on these 2's, because I can't have two different state point 2's on one single problem, certainly not in one diagram. So we'll always use 2s to represent the ideal discharge from the compressor. S nominally stands for entropy, and we know that the entropy is constant if we assume that it's ideal, right? Now, again, I've shown this as a dashed line because that process doesn't exist, right? We're not actually going through a process from 1 to 2s, we're analyzing it. We're assuming that it exists just so we could use the right data in our isentropic efficiency calculation. But there's no such thing as that process from 1 to 2s. It's an ideal process. We're just people, right? We can't make ideal processes. So I'll show it as a dashed line. The real line goes from 1 to 2. And since this is the actual discharge from the compressor, I'm just going to use a subscript A. Different books write different things. Most books use 2s to represent isentropic. Some would just call this state point 2, just 2, or 2a like I've done. I prefer A, just so we have a distinction between the ideal point S and the actual point A. All right, so that's our work input as we go from 1 to 2. So there's my compressor work. Now I add heat up to point 3. So here's my heat input. And now I have the same thing between 3 and 4 as I had between 1 and 2. I will have to analyze it, assuming that it's an ideal process, as I expand through the turbine from point 3 to point 4. In fact, this time I'll just write 4s, right? We know that would be the ideal discharge, just a vertical line. And hopefully that's vertical. But in the real world, entropy increases. So we'll end up with a point 4, the actual point 4, which is going to be to the right of 4s. Okay, still on that pressure line, right? Still on the discharge pressure line from the turbine, the P minimum line, but still at a different point. And then we go from 4 actual back to 1. Let's not forget to write my turbine work output, and then also the heat rejection or heat output from this particular cycle. So this is what, well, the TS diagram would look like for this particular case. Okay. A simple but non-ideal Brayton cycle. All right. So with this in mind, what are the equations associated with this particular type of process? Well, the equations aren't a whole lot different. We would still note that the heat input is still just going to be the heat input from 2 to 3, although I can't just put 2, I have to put 2a. So the actual heat input is from 2a to 3. So this is just H3 minus H2A. Okay. So these are, again, just the general equations which will apply to the case of variable specific heat. So maybe I'll put variable specific heat. So if we use variable specific heats, then the heat input is just found by finding this enthalpy change. We know that the work input to the compressor is also just the enthalpy change, but again, it's from 1 to 2a, not 1 to 2 or not 1 to 2s, so we'll just write this as H2a minus H1. We also know that the work out from the turbine is from 3 to 4a. So that's another equation that we're going to have to utilize. And of course, the thermodynamic efficiency is still just the net work divided by the heat input. So it's just a matter of putting all these various enthalpy terms into the equation below. So H3 minus H4A minus H2A minus H1 divided by H3 minus H2A. Okay. Now, certainly there are ways to adjust this equation. I mean, there's an H3 minus an H2A in the numerator. I suppose if you wanted to, you could just write this in its alternate form. Just collect the H3 and the H2A terms, and that just becomes 1. And then we're going to subtract from that, well, what do we have left? H4A minus H1. And then in the denominator is still H3 minus H2A. And in fact, H4A minus H1, isn't that the heat output? And isn't H3 minus H2A the heat input? And this just tells us that this is the other pretty common form of the efficiency equation, right? Instead of net work over heat input, another way to write it is just 1 minus heat output over heat input, which is exactly what this is. So that makes sense. So those are the equations we're going to utilize. Now, again, we're going to have to use isentropic efficiencies. We're going to have to use, because we're now talking about variable specific heats, we're going to have to use the relative pressure data. So you're still going to have to use that. So remember, the pressure ratio, which is P2 over P1, is still equal to PR2 over PR1. But we have to be really careful here. I can't write any 2's. I mean, I could put P2 because I know there's only one discharge pressure from the compressor. I could call it P2A, call it P2S. I'll just call it P2. But the relative pressure, when shown in this context, only applies to the isentropic process, right? I can't use this to go from point 1 all the way to point 2A. This only applies from 1 to 2S. So this really now has to say that the pressure ratio equals PR2S over P1. Okay. Now, we're going to know the pressure ratio in most problems. We're going to know the inlet temperature, because that's just the ambient temperature. So we can look up PR1. We can find PR2S just by using this equation. And then once we have PR2S, then we could go back into our property tables and get the enthalpy at 2S. So now we're going to use PR2S in table A17 to get the enthalpy at 2S. And then once we have the enthalpy at 2S, then we just have to go back to our compressor efficiency. Our compressor efficiency is defined as the ideal amount of work associated with that compressor over the actual amount of work associated with the compressor. And of course, the ideal work is just H2S minus H1, and the actual work is just H2A minus H1. And you're going to now use this to solve for what's now going to be your only unknown, which is your enthalpy at 2A. So we use this in order to get the enthalpy at 2A. Okay. So there's your enthalpy at 2A term. It's going to be there. And then further note that the same thing applies to the turbine, right? We're going to also have to use the fact that the pressure ratio equals P3 over P4, which is PR3 over PR. But this time, let's make sure we write down the 4S. I don't need to discuss it so much. I mean, we talked about it over here for the compressor. Now we're looking at it with regards to the turbine. But this would be the ideal discharge from the turbine. And then we're going to use our PR4S. This is going to be the unknown from this equation, right? We'll know the pressure ratio. We'll typically know our temperature at point 3. That represents the maximum temperature in the cycle. That's the temperature achieved by the combustion process. It's a design temperature limit that the designers will definitely know in designing the combustion turbine, which is another name for these gas turbine engines. So T3 is always known to us, right? You don't want to exceed T3. If you do, you might melt the entire engine. Or these days, a lot of engines are made out of composites. They don't really melt. They just essentially turn to dust and disintegrate. We don't want that. Anyway, we're going to use PR4S in order, that is in table A17, in order to get H4S. And then we have our turbine isentropic efficiency. Now keep in mind that the definition of isentropic efficiency for a work output device, a turbine, is the inverse of that for a compressor. It's the actual work over the ideal work. So the actual work is going to be H3 minus H4 actual. The ideal work, H3 minus H4S for ideal. And we'll already know from above H4S, we'll know H3. There's only one unknown, which is the actual enthalpy coming out of that turbine. So we use this in order to get H4A. Okay. So now we have all of our enthalpies, and we can now find the thermodynamic efficiency, or really any other data or properties that we need. So any questions at this point? Okay. Which really then just leaves us with one more special case, which is now constant specific heats. Okay. So let's note first of all that no need to change my diagram, no need to change the schematic diagram or the realistic diagram. We're only changing our methods of solution, so nothing really changes. Also, let's keep in mind that these general equations from variable specific heats came from the first law of thermodynamics. They still apply. The only difference is, of course, we're going to replace the enthalpy change with Cp times the temperature change, just like we did a few minutes ago for, well, for the ideal cycle, right? Nothing has changed. So let's just rewrite some of these terms. The heat input is now going to be Cp times T3 minus T2A. The work input, which is our compressor work, is going to be Cp times T2a minus T1. Sometimes you can put a subscript a next to this. I mean, like I've done over here. If you just want to remind yourself that this is the actual work, it's not absolutely necessary, but it doesn't hurt. So WCA. The work output is the work produced by the turbine. Again, this is the actual turbine work. So this is CP times T3 minus T4A. And then, of course, the equation for thermodynamic efficiency isn't going to be really any different. So the thermal efficiency is still just the net work over the heat input. In other words, the turbine minus the compressor work over the heat input. So again, we could just plug in all these different terms from above. Please note that you're going to have a CP term in all terms in the numerator and denominator, so they're just going to cancel out directly. And we just get T3 minus T4A, and then minus T2A minus T1. And then just divide this by, well, it would be the heat input term in the denominator, T3 minus T2A. Okay. Now again, if you want to, you can see there's a T3 minus minus T2A term in the numerator as well as the denominator. So if you wanted to, you could manipulate this a little bit, but frankly, generally we're not going to. So why don't I just leave it in this particular form, and that's then how we would find the thermodynamic efficiency. Now you might wonder, well, is there a simplified version of this equation that would allow me to find the efficiency only as a function of the pressure ratios? And the answer is simply no. You can't do it that way. Okay? These are non-ideal processes now. We absolutely need to find the temperature, the actual temperature, leaving both compressor and the turbine, and we have to use those temperatures directly in these various equations. Okay? And then one other thing just to point out, in the same way that we used relative pressures to deal with the isentropic efficiencies of both compressor and turbine, we're not using table A17 anymore, right? These are ideal gas constant specific heat problems now. So we're just going to have to use the equations, right? Again, the same kind of equations that we just looked at a few minutes ago. So again, let me just make this note. So the temperature ratio from 1 to 2 is going to be equal to the pressure ratio raised to the k minus 1 over k power. Okay. And in fact, this isn't quite right yet. We can't just leave point 2 hanging. It's either 2s or 2a, and clearly this only applies to the isentropic process, right? I mean, this equation was specifically derived for an isentropic process involving an ideal gas with constant specific heats. You can't use it for the actual process. So this is actually T2s over T1 equals a pressure ratio to the k minus 1 over k. Okay, so this equation will allow us to find T2s, right? And then we want to use the compressor's isentropic efficiency equation. Now, again, the isentropic efficiency is the ideal over the actual work, but those work terms are really just enthalpy change terms, right? We know that now. And of course, we know that the enthalpy change is just Cp times the temperature change, and we have Cp in numerator as well as the denominator. So the Cp's are going to cancel, and this is only going to be a function of the temperatures. So this is just going to be T2s minus T1 over the actual temperature at point 2 minus T1. And we use this in order to find T2 actual. And then once we have T2 actual, well, that's something that we're then going to use directly in our equations, right? Either for work or heat input or thermodynamic efficiency. And similarly, for our turbine, we know that T3 over T4s is going to equal the pressure ratio raised to the k minus 1 over k power, right? So we're going to use this in order to find T4s. And then we use the turbine's isentropic efficiency, which is now the actual over the ideal work. And of course, the actual work is just the enthalpy change, and enthalpy change is Cp times the temperature change, and the Cp's cancel and everything I mentioned just a moment ago. So this then just becomes T3 minus T4 actual over T3 minus T4s. And we use this to find T4 actual. And then having T4 actual, well, again, that's the last thing we really need. And we can calculate any other terms that we need. Work, heat, efficiency. And of course, any of these terms, or I should really say all of these terms, we could multiply the mass flow rate by the Q or the W terms, right? The Q or the W terms are lowercase, right? They're per unit mass. So if we simply multiply them by the mass flow rate, well, that gives me the heat input rate, right? Heat per unit time, or work production rate, that is power per unit time. So every one of these equations we talked about today, that is the Q and the W equations, could certainly be multiplied by a mass flow rate in order to get power or rates of heat transfer, which is, again, another thing that we would often see in these various problems. So I'm out of time. Next time I'll go through an example problem. And have a good one. Please don't forget to bring your homework with you next time. Also, I do have a couple of old homework sets here, Mumby and Sargesian. And also, remember, I've assigned new homework for the week, so don't forget to write it down. Anyway, see you guys on Wednesday.